All right, everybody. For those who are just tuning in today, we've had an ongoing student and postdoc poster competition all week, and the winners were announced yesterday and were invited to present their poster as a short talk today. So we're very excited to have Sebastian Sieber tell us about the exocomets discovered by TESS around Beta Pictoris, or at least light curves of them. So Sebastian, are your slides set up for first? All right, let's see what slides we get up. Yep, there we go. So you're mic'd up, or do you want to use this one?
I will use this one.
Okay, great. So you have 5 minutes,
Yeah,
and
sure.
the clock is down there.
Thanks. So, hello everyone. So, I will talk about my poster. It's about transiting exocomets detected by TESS in the Beta Pictoris system. It's based on a letter we recently published in ANA. And Beta Pictoris is a really interesting system because we know it has at least one planet which was observed directly. And it's also interesting for astroseismology because it's a so-called Theta Scuti star. So it has pulsations. And it's also a very bright star. It's about a 4th magnitude star, and it's fairly close, about 20 parsecs away, which is more or less 60 light years. And it's a very, very young star, so only 20 million years old. And so already in the 80s, we had observations by the IRIS satellite, and it told us basically that it has an infrared axis and a dust disk. And a few years later, we had observations in spectroscopy and indications that we have exocomets in the system and evaporating gas from those exocomets, which produce those signatures in spectroscopy. And a few decades later, we had observations by TESS. And TESS observed Beta Pictoris for 4 sectors, so a little bit more than 100 days. And it was one of the pre-selected targets to have 2-minute cadence observations. So this was really interesting, and I had a look at the data. So I looked at those 4 sectors, and I just picked out here those 2 sectors, Sector 5 and Sector 6. And there wasn't really anything interesting in Sector 4 and 5. You could still do astroseismology, but Sector 6 was really interesting because you were able to see this dip here, but I didn't know what it was. So I just went on, I did a mask, I just removed it, and I did astroseismology. I subtracted those pulsations, so I first extracted about 50 pulsations, and I extracted those pulsations, and I subtracted them from the light curve. And if you do that, and if you look again at this dip here, you will see, so that's my badge, if you subtract the pulsations, you will have this signature here. And this signature is now much more visible. And if you go back to Sector 5, you will see 2 other events, which are weaker, but still clearly visible. And they are non-periodic. So this was really interesting. So I started obviously to check the data release notes, what everybody should do working with TESS data. The next thing was I checked instrumental effects like momentum dumps and so on. I also checked stars in the vicinity if they have something like this, so a similar event like this, but this wasn't the case. And I also checked stars in the background, so stars in the aperture. But none of the stars in the aperture were bright enough to create such a dimming event. So this was basically the work of one Wednesday afternoon or Wednesday night in March. And on the next day, on Thursday, I went up to my group meeting and I showed it to my colleagues, what I have seen in the TESS data. And it was fairly obvious for everyone what it would be or what was the cause for this event. Aliens, obviously, but none. So we contacted colleagues in the Netherlands and the UK, and they told us about a very interesting publication 20 years earlier by Le Cavalier in 1999, and they modeled how such an event would look like, a transiting exocomet in the Beta Pictoris system. And if you look at our observations now with TESS, it's really similar. So the goal finally is obviously to see something like this again in the extended mission of TESS, So we're really happy that TESS was extended, and to observe at the same time in spectroscopy to learn more about the composition of exocomets. Thanks.
We have time for some short questions, and Avi's just sourcing some microphones. So think for a second of a really good question for Sebastian about exocomets around Beta Pic. Get it in your brain. We want questions from everyone in the audience. Everyone's welcome. Maybe. Okay, we have a question. I will bring this one. Take that one again.
Yuta, not from University of Colorado Boulder. I'm not familiar with this field, so a basic question. Are there any difference in, depending on the wavelengths and how deep or how long?
Yeah, so TESS was only looking at this broad light region. But yeah, Le Cavalier did an analysis with different wavelengths, and it would look different. So, for example, in spectroscopy, we see those signatures from those exocomets, and those signatures are really moving pretty quick because of the redshifting, the movement of the comets at the end.
Ed Ginsberg from UMass Boston. Since Beta Pictoris is such a young system, how do you know that this is a comet and not, say, an asteroid or a chunk of a planetoid or something like that?
Yeah, so that's a good question. For example, something like an evaporating planet would probably move much quicker around the star, and we calculated the transverse velocity, and it's much slower than that.
Last one.
Elizabeth Matthews, hi, I'm over here. You talked about re-observing this during the extended mission, but are there also plans to look for other similar similar dips in other systems known to have disks? I think that would be really interesting if it's possible.
This would be a great project. Somebody could do this, to check all the systems with edge on disks at the end, yeah? Great idea.
You're not planning to?
Okay, let's thank Sebastian again. Our next speaker is David Martin, who's going to tell us about circumbinary planets with TESS, so you'll have 5 minutes.
Wonderful, thank you very much. Alrighty, how do we form super Earths? How do we form mini Neptunes? So they're the most common planets we know at short period, yet there remains this ongoing tension between whether they formed at these short periods or if they migrated inwards. Now, I don't have all the solutions to this problem, but I do have potentially a new way at looking at this. That is to say, what if I told you I could actually turn off in situ formation? Now, in fact, nature does this very efficiently. It does this by simply adding in a second star. Binary stars are very common, and we've known for a while that a binary star will carve out a huge hole in the disk, so the planet's not going to form there. We also know that even if you're in the disk, but in the sort of inner regions, you're not going to form there either. It's a very unhospitable environment to form a planet. But we know that you can actually form it far away in the disk, at which point we expect the planet to migrate in and then stop near this inner disk cavity, and we've both predicted this and seen this in the data. So it gives you this sort of tantalizing possibility of, well, if these are the planets we see around single stars, what do we expect around two? Do we expect to see the same thing? Do we expect to maybe get rid of that gap? Maybe we'll only find the mini Neptunes, or maybe we'll only find the super Earths, potentially giving us a difference between the two. Or maybe small circumbinary planets are rare, which is something in of itself. Ultimately, to answer these questions, you have to be able to find these planets at all sizes, and the existing detections have only been sensitive to giant planets. We have this entire unexplored region here. And the reason why we've only found giant planets is quite simple, because this planet is transiting a moving target. And so you have this huge range of potential transit positions, and hence a huge range of potential transit times. And to further complicate things, the planet is on an orbit that is dynamically varying. So if you want to get phase-fold transit times on a single period of a single duration, you're in trouble because the TTVs are days, not seconds, not minutes, not hours, but days, much longer than the transit duration, which also, just to complicate things further, varies as well. So the old method could only pick out systems where each individual transit was individually significant, and this means you get gas giants. So the work I've been doing has been trying to get a new algorithm where you can actually fold on this variable period with variable durations to pick out shallow transits and get small planets. I'm going to show it in action for a very simple system. This is Kepler-16, where you can see the transits by eye are very, very obvious. We use an n-body algorithm to predict the exact time and duration of each transit. Now, the transit time is predicted at the exact middle of each of these windows, but you see the actual transits are a bit off. So we let the algorithm kind of like smear it around side to side, and this is very important because it allows your input parameters to be a little off. It allows your search grid to be a little coarse, and this is important because this is an n-body. It's quite a slow process. We fold, assuming that we get this variable transit timing. You see that the interval is changed by about 8 days here. And you scale by a variable duration, and voila, here's your discovered planet. Now, obviously, Kepler-16, very easy. If we go a bit harder, Kepler-47. Now, this is at, I'd say, the limit of the by-eye detections. We've got very trained eyes here. We can see these transits, but it's kind of at the limit. And this is the smallest circumbinary planet found to date, at 3 Earth radii. But the algorithm is able to actually pick out these individual transits. But now the step that we're really working on now is to say, can we probe into that unknown parameter space? I.e., can we get small circumbinary planets? So we're doing this, testing it with injection recovery. This is a 1.5 Earth radius planet. And these transits look kind of crappy individually. But if you stack them all together, they actually do form a significant signal. And I know exactly where these transits are because I did inject them. But of course, the search itself is very tough. It's a needle in a haystack. You have to search over this entire parameter space, running an n-body on each set of parameters. And it's not just 2-dimensional here, it's more like 10-dimensional. And all you're getting is this tiny little blip where your template matches. But okay, right now, we're working on it with Kepler because we really appreciate these long baselines. This code then will be released to the public, so particularly for TESS, particularly with the continuous viewing zone, we can all have fun finding circumbinary planets and hopefully answering some of these questions. So I'd like to finish by thanking my collaborator, Dan Fabrici, who's not pictured here. Dan is a human, but I'll also thank my dog, whose presence on the poster is probably why I won. Thank you very much.
Thank you, David, and thanks to your dog. Questions for David about looking for circumbinary planets? I have one. I'm going to assume you're familiar with the CATS algorithm,
Yes.
QATS. Can you compare and contrast what you're doing to what that algorithm does?
I think the CATS algorithm tries to be a bit more clever than I am. Mine is a very brute force approach, and it's an approach which up until a year ago I thought would not work. But by being a little tricky with the search grid you search over, I've suddenly been able to take the problem down from taking the age of the universe to taking, days or weeks.
So it's to do with the increase in computational efficiency.
Something like that, yes.
Okay.
Hi, David. Luke Bauma, Princeton. Could you please comment on how the noise floor changes with your search algorithm compared to the sort of standard BLS?
I can't give you exact numbers. This is the type of comparison I haven't been able to make yet. I do think we're not going to be able to get exactly to what you can do around a single star. One of the additional issues is that binary stars are a bit of a pain to detrend. You've got obviously 2 signals of variability, you've got ellipse order variation, eclipses, and also that transit duration, which varies so much, means that you have to detrend on a variable window to make sure you don't clip off the long transits. So all of this put in together, I don't think we'll be able to match BLS around a single star for comparable brightness, but hopefully we can get close.
Last question? Yes, one thing that makes it more difficult
Who
to
are
find...
you and where are you from?
Oh, yes, John Jenkins, NASA Ames Research Center, sorry. One thing that makes it difficult to search for planets around circumbinaries is systems is eclipse timing variations, and so can those provide some clues for you in terms of your algorithm and finding planets?
It's a very interesting possibility. The difficulty, though, is that the eclipse timing variations, since these are dynamical ones, scale with the mass of the planet. And so even in those dozen giant planets we've seen so far, only about half of them have measurable eclipse timing variations, which let you get the mass. So I don't believe we would see eclipse timing variations for smaller planets. And indeed, the algorithm doesn't take that into account. But even then, the eclipse timing variations would be on order of tens of seconds, maybe. So we're talking much less than a cadence.
Great. Let's thank both our winners again.